My name is John Sloan, and I'm going to talk today about time and space. It was really how I got interested in how timekeeping and navigation are sort of inextricably linked together. I've been interested in timekeeping for a long time, but that would be a whole other lecture, particularly precision timekeeping. And of course, you guys deal with GPS and geolocation in your own products. This is my standard disclaimer. I'm a product developer. That's what I've been doing for about 40 years now. I'm not a rocket scientist, and I'm not a nuclear physicist, and I'm not a horologist, which is what we call a clockmaker. But all of those areas, one of the great things about product development is all of those areas somehow impinged on the products that I was developing. And so that's how I got interested in this stuff. So everyone's already tired of hearing this tick. This was for ages 6 and up, and I managed to get it put together and working. This is a real, actual mechanical pendulum clock. I wouldn't rely on it to get up to go to work, but it actually does keep time. And what's interesting about this clock, if we look on the back of it, is you see all these gears. That's what we associate with clocks, right? We think of gears. That's actually the least interesting part of any clock. The gears in this clock are nothing more than a kind of analog divider circuit or a mechanical divider circuit to divide down into seconds, minutes, and hours, and that's all it is. So I'm going to set this up here for just a moment, and hopefully I've disconnected it so it doesn't run. So when we talk, and Joe's just going to have to bear with me because I use like the whole whiteboard here, okay? So when we talk about time, what's interesting is we're actually talking about 3 fundamentally different things. And if you don't believe me, look at the Linux system calls or the newer POSIX API, the library calls. They're actually completely different for these 3 things. We're either talking about time of day, which me and IBM both abbreviate TOD, and that would be like 1300 or 1 p.m., depending on your loyalties. Or we're talking about duration, which is hours, minutes, seconds, and so forth. Or we're talking about frequency. And we don't even realize often that we're talking about frequency. But these things are all defined in terms of each other. So for example, what's 1300? It's 13 hours after midnight, which we've decided that's when the day starts. 1 p.m., before we had time zones, was 1 hour after solar noon, which is when the sun is at its peak in the sky. So every place had their own sense of what noon was. And so those are defined in terms of durations after some other point in time. And then, well, okay, so 1 p.m. is an hour after noon. What's an hour? Well, it's 60 minutes. Well, what's a minute? Well, it's 60 seconds. Well, what's a second? Okay, that's a little bit more difficult. What is a second? We define our units of time ultimately all in terms of frequency sources. And the hardware guys would call this a frequency source an oscillator. I like the term frequency source. That's actually what a lot of clockmakers call it. But the fact is, that's really where we fundamentally get our sense of time. For example, this clock has an oscillator in it. Specifically, it has a 4 Hertz oscillator, a mechanical oscillator. And that oscillator consists of the following parts. And I'm going to tell you right now that every oscillator we look at today, we're going to look at several, every oscillator we look at today is going to have these 3 parts in it, although they may be implemented differently. But I'm very tempted to say every oscillator that exists, every frequency source or that will ever exist has these 3 parts in it. So first of all, it has a power source. And on this one, it's the mainspring, which is this part right here. It's a tightly wound metal spring inside what a clockmaker would call a barrel. Springs are actually kind of dangerous, so they enclose them so they don't take a finger off. Okay, it's just that simple. It has a resonator, which is a natural source of periodicity. It just reminded me that I didn't turn my thing off, my phone off. A natural source of periodicity. That is, we somehow draw some periodic behavior out of nature. And of course, in this clock, it's the pendulum. The thing about pendulums is, and this is like a law of nature, is the period of a pendulum, the time it takes to swing back and forth, doesn't depend on its weight, or what it's made out of. It depends solely on its length. That's all that matters. Its weight or its mass or what it's made out of determines how much energy it can store, how long it can keep running before it runs down. But its period is based on its length, which is why mechanical clocks have pendulums that come apart. So you can adjust the length to tune the clock, and that's how you tune the clock, a mechanical clock. One way you do it. And a mechanical clock has an escapement. And the escapement is kind of hard to see, but it's this little wheel right here, just like that. And it's this little thing that kind of looks like a seesaw when it's running. Because the way this works is the pendulum is connected to this little pin right here. And so the mainspring keeps this, which is called the escapement wheel. It's not a gear, it's a wheel. I'll tell you more about that in just a moment. It keeps this under constant tension. If it weren't for the rest of this mechanism, this would just spin out of control and the clock would fly apart and the mainspring would run down. But the escapement's called an escapement because it allows the energy of the mainspring, the power source, to escape a little bit at a time. And I know this is hard to see, but this is how this works. This is under constant tension of the mainspring. And what happens is the pendulum swings and brings this little teeter-totter called the escapement anchor down against this gear and stops it. And then the pendulum swings the other way, lifts it up, and for just the briefest moment, the escapement wheel isn't constrained, and it turns just enough to turn one tick, and then this comes down and blocks it. So it's teeter-totter, teeter-totter, tick-tock, tick-tock. So when you hear a tick-tock, it's actually the teeth of the escapement wheel slamming into the teeth of the escapement anchor as it teeter-totters back and forth. But there's something much more subtle going on here, okay, that's not so obvious. The clock is not a perpetual motion machine. That something must be putting energy into that pendulum to keep it running. And because of the weird little shape of these teeth, they sort of look like predator's teeth. They're kind of curved, kind of a compound curve. As it's coming up, it actually gives a little push to the tooth on the escapement anchor, which makes the pendulum swing this way. And then as the pendulum unlocks it and allows it to turn, and it locks the other way, when it lifts it up, the shape of the tooth gives this a little push, which pushes the pendulum in the other direction. So the pendulum is locking and unlocking the escapement, but the escapement is pushing against the pendulum in both directions. That's what keeps the pendulum running. This is really important because this is a positive feedback loop. And so everything we're going to look at today has these three parts in it. In fact, this is so important, I'm going to challenge Joe with the camera. I'm going to put it way over here. And I'll sort of abbreviate these. So everything has a power source. It has a resonator, which is the natural source of periodicity, something we draw from nature. And it has a positive feedback loop. So let's look at another one. This is a $26 pocket watch, which runs most of the time. I'm going to pass this around, and so if it's not running, don't be afraid to give it a little tap. And so I've actually marked this. This doesn't have a pendulum, because pendulums really have to remain upright and still to work correctly. This has a balance wheel. A balance wheel's period depends on two things. Its moment of inertia, which is how mass is distributed around its axis of rotation, and the spring constant of a hairspring. And so instead of pushing on the pendulum here, this still has a mainspring, and it still has an escapement, just like that clock. But what the escapement does instead is it pushes the balance wheel in one direction, and then the mainspring brings it back, and then it pushes it in the other direction, and then the mainspring brings it back again, or the hairspring, sorry. So you can just go ahead and pass that around. And in fact, for those of you that still wear watches, the proud, the few, the brave, your Quartz watch, it's probably a Quartz watch, your Quartz watch has these components in it too. And I'm going to terrify the hardware guys by actually drawing some stuff up here, but I'm not going to use actual hardware diagrams, so you don't have to worry about that. So quartz crystals have not a unique property. Lots of materials have this property. They're piezoelectric, And if you don't like that pronunciation, the dictionary has 3 others for you, but that's how I choose to pronounce it. Is piezoelectric, which means when we take a quartz crystal and we subject it to mechanical stress, we press on it, or we torque it, or we shear it, okay? It generates a voltage, and when we let it go, that voltage goes away. So we can generate pulses of voltage just by pressing on the crystal and releasing it. And that's fundamentally how quartz crystals work. It turns out if we take a tiny little bit of quartz crystal and we cut it in the form of sort of like a tuning fork, and we put some electrodes on it, and we add an amplifier, and I imagine in the hardware world amplifiers look something like this. They go to 11, okay? Okay. And there's a lot of stuff here that the hardware guys know about, like capacitors and stuff like that, that I, software guy like me, I just don't deal with. But what happens is, we stress the quartz crystal and it generates a little bit of voltage, and then it returns, and that voltage pulse goes through the amplifier, comes back around and gets applied to the quartz crystal, which causes it to form and to snap back again, which generates a little voltage pulse, which comes around and goes back into it again. And in fact, if you're very clever about how you cut and where you cut these quartz crystals, you can get them to vibrate because of this voltage pulse traveling around through here in a very regular manner. And in fact, your quartz watch almost certainly has a quartz crystal that vibrates at 32,768 hertz. And everybody's ears perked up when I said that, because that's a power of 2. That's not an accident, because it's very simple to make a simple electronic counter that advances the second hand on your watch every time it overflows. Okay, and it's just that simple. That's really all there is to it. I forgot to mention that mechanical watch has a 4 hertz or a 6 hertz oscillator in it. So this is a quartz watch, quartz crystal watch. It's a really big one, but I like it because it's clear. You can actually see it. And if you push the little button that has the arrow on it, hopefully it lights up with a time, 12:15. Okay. And this has all of those components on it. It has a power source, which is the battery. It has a positive feedback loop, but you can't really see it because it's inside a chip. So I marked the real-time chip there that this is in. And it has this tiny, tiny, tiny little metal can in it, which has a quartz crystal with electrodes on it that is cut in the shape of a tuning fork. And this is not microscopic. Don't ask me how or why, I know this, but you can in fact take a Dremel tool to one of these and open it up and take the quartz crystal out and look at it. It's about that big, but you can see it. Okay? And so this little device has all the stuff I've been talking about in it. And don't be afraid to play around with the buttons on that to get it to display something. But look at the metal can, the little tiny metal can. So that's time. Now we need to talk about place. So the ancient Greeks, as far back as 400 BC, knew that there was some connection between timekeeping and navigation. They just couldn't quite get a handle on it. They didn't quite have the technical expertise to figure that out. But they knew, because of the way the stars changed in the sky at night, and because how that looked different when they traveled, because they were great sailors, they understood there was some connection between the passage of time and navigation. But we didn't really figure that out reliably until the mid-1700s, about 1759. And there were a lot of ways that people sort of decided how might be a good idea to determine latitude and longitude, but by far the most accurate way we did it was by timekeeping, by having accurate clocks. So latitude is sort of interesting. Latitude is your position north or south of the equator. So it's 90 degrees north up to the pole and 90 degrees south. The equator is sort of a natural point from which to measure latitude. And it turns out, because the Earth changes its position on its axis with respect to the sun, if you simply have a very accurate clock, accurate to within a few seconds a day, which was a challenge in the 18th century, but possible. They solved that problem. If you had a very accurate clock and you merely looked at the time when the sun set, or when it rose, or when certain stars rose in the sky, you could determine your latitude by looking it up in a book. And this is a book that has, for every day of the year and for several hours during the day, it says if this is when the sun is rising and setting, this is what your latitude is. And then you could interpolate between the numbers on here to figure out where you were. This book has been in constant publication by the Royal Observatory in Greenwich, England, since 1767. Okay, because astronomers could figure all this out well in advance. Okay, just because the Earth and the Sun were such regular frequency sources. But longitude was a little harder because the Earth insists on spinning on its axis every 24 hours. And that's a really fast change, actually, if you're trying to figure out where you are. Particularly because if you were sailing, let me just pick a point at random here. Oh, the port of London right here, and you were making a 6-week sea voyage all across the Atlantic Ocean, in which there is nothing to see out there. There is no landmarks. You're totally relying on celestial navigation to figure out where you are. And your goal was to get to here, which is what they called the West Indies, because Columbus thought he was in India when he landed. But in fact, today we call the Caribbean. That was like the money route in those days, because all the wealth of the New World, or a lot of it, was early on, was funneling through ports that were set up in the Caribbean, okay, by all the major sea powers. And so there's a lot of money going through here, which is why there were pirates in the Caribbean. Okay, that's not. There's a reason for that. Okay, that's where all the money was. So longitude was a little harder, but they sort of realized a couple things. Number one is there are 24 hours in a day. The Earth rotates and returns to a position every 24 hours. And there's 360 degrees, which is how we keep track of, in a circle, which is how we keep track of longitude. And those two things are sort of the same thing, right? 360 degrees around, 24 hours around. So, if you were to take a highly accurate clock, a really, really accurate clock, accurate to within a couple seconds a day, and you went to the Royal Observatory, which is where we're going to measure longitude from, because there is no natural point on the Earth like there is on the equator for latitude. So we have to arbitrarily pick one. So of course, being members of the British Empire, we're going to pick the zero meridian to pass through the Royal Observatory in Greenwich, not Paris, as the French would have you believe, but Greenwich. And we take our marine chronometer, which is our extremely accurate clock, and we take it to the Royal Observatory, and we set it to the average time of all the even more accurate pendulum clocks, what they call regulators, in the Royal Observatory at Greenwich. In other words, we would set our clocks to Greenwich Mean Time, and then we got on our ship and we sailed out of the port of London. Then every day, for example, take the simplest case, when it was noon, when the sun was at its peak, at noon of the solar day, the local time, we would have to just look at our clock, and we would look at the sun and say, well, it's noon local time, but it's 7 p.m. in Greenwich time. And we could subtract that in simply using this conversion, subtracting that time difference by the number of seconds in a day, multiplying it by 360 degrees, we would know where we were, our longitude. It was just that simple. Everything else, like sextants and so forth, are all special cases to like measure the angle of the sun when it's not directly overhead, so you don't have to do this at noon. Or to measure the pole star, the North Star, which is another way of doing this. But it all has to do with this conversion between 24 hours and 360 degrees. And so, when you were sailing across the Atlantic Ocean and you were wondering if you're getting near the Caribbean or not, you would look at your clock and you would realize, wow, the local time is noon, and that appears to be just a smidge over 5 hours, about 5 hours and 11 minutes past Greenwich Mean Time. I would do this conversion and realize that that translates to 78 degrees, which is in fact the longitude of the Caribbean islands. And so I would know that I was in fact going to be very closely, very soon inside of land. Okay, and that's exactly how it worked. So longitude and latitude, though, aren't the only things that use time. In fact, this keeps cropping up in history over and over again. Foghorns. If you were on a local ship just going port to port along a coast and it was nighttime or foggy, you would really worry about running into the shoals near shore, okay, particularly as you were coming into port. So you would listen for the foghorn. Foghorns ran on clockwork automation. So if you carried a clock on board that was synchronized to the clock on shore at the foghorn, you could say, oh, foghorn, it's 2 minutes after midnight. You could do a calculation with the speed of sound, which they knew, and calculate how far you were from shore. So you knew whether you were keeping it away from the shoals or when you're coming into port and so forth. And that's exactly how they did it. In the mid to late 1940s, right around the close of World War II, LORAN was developed, which is an acronym meaning Long Range Navigation. And LORAN works something like this. If you had a coastline, you would have a master transmitter and several slave transmitters. Oops, try two there. And on your aircraft or ship, you would have a receiver and an oscilloscope. And when you got transmissions, the little blips from these guys, you would see little blips. These are far cleaner than they would ever actually look on the LORAN oscilloscope. That was by far the most challenging part of this. And the distance between these blips weren't how far you were from the transmitter, it was your relative distance between the two. If they're right on top of each other, given the speed of light, you must be the exact same distance between the two transmitters. Well, if you're exactly the same distance between these two transmitters, then you must be on this line somewhere. You don't know where you are, but every point on this line is equidistant from these two transmitters. It turns out if you're a little closer to this one and you plot all those points, it's a hyperbola. And the closer you get to this one, the more acute that hyperbola gets. And of course, there's another set of hyperbolas over here. And you can do the same thing for these transmitters. And so you would do this for two pairs of transmitters and then overlay those charts on top of each other. And at some point, the two lines you drew would intersect, and that's where you were. And that was hyperbolic navigation. And that actually worked really well up until we had alternatives for that until the 1970s. And this is a lot easier than it looked because they had charts with these hyperbolas on them already. So you didn't have to draw those, you just had to look them up. The hard part was reading the oscilloscope and figuring out what it was telling you. So the fact that we have this long history of using timekeeping to keep track of where we are, then it should be no surprise that that's exactly how GPS works too. So GPS came along in the 70s. It's been around for a while. And originally, there's several GPS systems in orbit right now. Well, us and the Russians, and there's some partial ones. It used to be called, our system used to be called Navstar GPS, but now we all know it just as GPS. And this is my little Lego model. It's the only model I could find of a GPS satellite. There are several models or generations of GPS satellites in orbit. This one is a block, what's called a Block 2F, IIF, okay, Block 2F. It's just sort of a model or generation number of it. And to give you a sense of scale, on the actual satellite, the main body, this yellow part called the bus, that's 8 feet high. So this is big. And the entire spacecraft in orbit weighs 3,600 pounds. These are big pieces of kit. Okay, these are large satellites. There are currently 31 operational GPS satellites in orbit, of which we only actively use 24 at a time. And of all those satellites, 12 of them are the Block 2F model. And every GPS satellite has multiple atomic clocks in it. The 2F model specifically has 2 rubidium clocks and 2 cesium atomic clocks. And we'll talk about those very shortly. And every 30 seconds, every GPS satellite transmits a bunch of stuff actually, but the two things we care about right now is it transmits its ephemeris, which is a description of its orbit, a sort of a mathematical description of its orbit. It's like, at this time I will be here, okay? And it transmits a timestamp. And that's really all there is to it. From that, we can do all our navigation with GPS, with a description of its orbit and a timestamp. Of the 31 satellites that are in orbit, generally, if you have a clear view of the sky, you can see as many as 9. That is your GPS receiver. I can't see any through your energy-efficient windows, unfortunately. So, because I've tried that. But generally, you can see up to 9 satellites, and you need 4 to do a solution, a mathematical solution for your position. And it's all, as you guessed, it's all time-based. So, if you have a GPS satellite, and it transmits a timestamp, when your receiver picks it up, your receiver compares the GPS time to its time, and it knows the speed of light. So it knows its range from the GPS satellite. These GPS satellites are in 6 different orbital planes, and a GPS satellite goes all the way around the Earth in about 12 hours. So there's a lot of them up there. It's kind of redundant, okay? But you know that you're on the sphere somewhere. You don't know where. Your receiver doesn't know where on the sphere, but it knows that it's this far away from the GPS satellite. And then it receives the same thing from a second satellite, and the intersection of 2 spheres is a circle. And a third satellite, the intersection of that sphere with this circle is 2 points. And then finally, the 4th satellite tells you which of those 2 points you're on, just from a timestamp and a description of the orbit. However, it's not that simple. It's not that simple because the clock inside your receiver is not an atomic clock, and it kind of sucks. And it may not even know what the time is. Maybe you've never set it. So even though if it were a perfect world, this solution would resolve down to a single point, it really resolves to a volume, right? Because they don't quite come together because the clock in your receiver is off. But so your receiver, the firmware in your receiver, really wants to solve this equation. Your position in space, x, y, z, and t, or x, y, and z, and how far off your clock is from GPS time, which is t. And so it receives information from 4 different satellites, so it wants to solve 4 equations and 4 unknowns. And there's actually different algorithms for doing this, but one of the common ones is to do a least square approximation that's iterative. And so your receiver does have some clues. Number 1 is it knows the time can't be any earlier than the time it received from this satellite. Maybe later, of course, the speed of light, but it can't be any earlier. Secondly, it knows that the clock in the receiver can only be wrong in 1 dimension. It can either be fast or slow, earlier or later, than what the GPS time is. It can't be wrong in any other dimension. That's it. And it knows you really were only in 1 place at 1 time when it took those readings. And so it begins to iterate on this solution, adjusting its internal clock in whatever direction makes this volume smaller. And it iterates, 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 and it iterates until it gets down to within the resolution of the GPS timestamp, which is at worst puts you in a space of about 15 meters across. And 2 wonderful things have happened when that happens. One is it knows fairly accurately where you are, but it's synchronized your really crappy clock inside your receiver to an atomic clock in the satellite. And that's really exciting because that atomic clock in the satellite is synchronized along with all the other atomic clocks and all the other GPS satellites, with an atomic clock at a ground station at an Air Force base near Colorado Springs, which is synchronized with a whole ensemble of atomic clocks in the Naval Observatory near Washington, D.C., which is synchronized with a really big, expensive atomic clock at the National Institute of Bureaus and Standards and Technology in just up the street in Boulder, which is synchronized through the auspices of the Bureau of Weights and Measures in Paris, with every other atomic clock in the world. That is pretty cool. And so, well, a lot of people are interested in the position fixing stuff. For a guy like me that has had to deal with products that needed really highly precise timing, having a really cheap clock that somehow has been synchronized to a vast network of super accurate clocks all over the world, that is a really useful thing to have. Okay? So, it used to be that organizations like AT&T, the big telecom companies, they actually owned atomic clocks, and they actually had them in their network. And in fact, even smaller companies owned atomic clocks just to provide a frequency source for their telecom equipment. But now, for a few $100s, you can just buy a GPS clock. As long as you have a view of the sky and a place where you can put the antenna, for a few $100s, you can build a clock that simply does this solution constantly for time and keeps its internal clock synchronized to GPS time. Or you could just do what I do and you could just build one. Okay. So that's all this is. This is a Raspberry Pi with a GPS receiver, which by the way is receiving GPS right now on this, and a real-time clock with a battery backup and an LCD display. Okay, really, I have far more. I have about $500 invested in this. You can buy a clock for less than that, a GPS clock. So, you know, unless you're me or you just like doing this, don't do this. Just go out and buy one. But I run a network time protocol daemon on this, and so this sits on my network. And so this clock is the second most accurate clock I have. This sits on my desk at home. It's my desk clock. I have a big GPS, bigger than those, a big marine GPS antenna sitting in my window office. Actually, I have 3 GPS antennas in my window, but that's beside the point. This is the second most accurate clock I own. And it's the second most accurate clock because it has one fatal flaw. If I lose the GPS signal for any reason, okay, if trees cover it, if the cats get in front of the antenna, if GPS is jammed, because it's very easy to jam GPS, this is no better than just a Raspberry Pi. That's all it is, okay? It really relies on getting those signals from space to synchronize its internal clock. So we really need to solve that problem, right? And to do that, we need to start talking about atomic clocks. So before we talk about atomic clocks, we have to talk about the fundamental way atomic clocks work, the thing that in nature that they rely on to tell time. And to do that, we have to go back to the year 1900, when scientists were shining lights on different elements just to kind of see what happened. And what they noticed is, for every element, when they shined a light of a certain frequency on it, it would apparently absorb that light, and then at a later time, and I mean later, like femtoseconds later, but at a later time, it would re-emit that light. And so something weird was happening inside the material. But what's even more interesting is every element was a little different. Okay? If there was something about the frequency of light that was unique to the element, that it would absorb, that the other frequencies, even off by just a tiny bit, it wouldn't work. But for if you could pick a specific element that they were working on, and for a specific frequency, it would absorb and re-emit that light in a very predictable fashion. But only that frequency, okay? That's kind of a lie. There were some resonant frequencies that worked too, but let's pretend only one frequency worked, because that makes the talk work better. So only one frequency worked. And so it took them a while. They called, light is a massless, photons are massless particles, and so their energy is not E equals mc squared, because there's no mass. Their energy is directly proportional to their frequency. So they knew this somehow, the material, the thing they came to call an atom, was somehow absorbing a very specific frequency, and therefore a very specific amount of energy. And they called this energy a quantum. Okay, so now you've all figured out what all this led to, right? It's a whole other branch of physics is what this eventually came down to. But it took them a while, but they eventually figured out that this is what was happening. And we're going to use as our example a particular element because it's fun to put actual numbers on this stuff. we're going to pick, not random, cesium, and we're going to pick a specific isotope of cesium, cesium-133. So cesium, which is abbreviated CS, cesium-133 specifically, a specific isotope, happens to be the only isotope of cesium that is not radioactive. Cesium's kind of nasty stuff, but cesium-133 is not radioactive, it's completely stable. It has an atomic number 55. And what that means is its nucleus has 55 protons, all mashed together with whatever 133 minus 55 neutrons is. And of course, neutrons are positively charged, so the nucleus has a positive electrical charge. And the nucleus spins like this. And like all electric charges that move, that generates a magnetic field. And if it's not an ion, it must also have 55 electrons, so the positive and the negative charges all cancel out. So it turns out, with cesium, it has 54 electrons in a bunch of, distributed through a whole bunch of orbital shells. And in the very outermost shell, it has the one lonely 55th electron. Okay, number 55 is all by himself in that outer shell. And of course, it has a negative electrical charge, and it's also spinning like this, not just smeared around in this orbital shell, but it's spinning like this. And so it also generates a magnetic field. And in your normal, everyday cesium atom, those magnetic fields attract each other. And life is good. It's just like this. Everyone's played around with magnets as a kid. These are really strong, by the way. I'm going to pass these around. Do not get these near your credit card or anything you don't want to wipe out. Okay. So it turns out that sometimes, not always, but sometimes, when a photon of exactly 9,192,631,770 hertz comes along and impinges on the cesium atom, it absorbs it and just disappears. Okay? But that energy has to go somewhere. And so what happens is, this lonely outermost electron flips its spin, flips the other direction. And the physicists in the room are going to have a stroke. But this is not completely metaphorically like taking one of these magnets, turning around and trying to put them back together again. Okay? So the spin and the magnetic field of the electron reverses, and it transitions. It simply disappears from this orbital shell and appears in a higher orbital shell. And at this point, we say the cesium atom has transitioned to a higher energy state. Okay, but this is not its natural state. It doesn't really like being here. It's not really not happy, and so it can't stay up here. So at some point in the future, as long as femtoseconds perhaps, but not zero, and some random time, we can't really predict when this random event will happen, this lonely electron flips its spin back the other way and transitions back down to a lower state. And so we talk about, somewhat metaphorically I believe, but you hear this all the time, you hear about cesium atoms vibrating. They absorb a photon, electron up, electron down, but energy has to be conserved. Okay, conservation of energy, and there's no losses due to friction here in this world. And so that energy has to go somewhere. And so a photon of exactly this same frequency, I'm going to say it again, 9,192,631,770 hertz, not a beat more or less, comes out, and it comes out in some random direction. No one can say where it's going to come out at. And now you know everything you need to know to build an atomic clock. Okay? Seriously. So this atomic clock that I'm going to draw is a cartoon atomic clock, by which I mean there's no atomic clock that actually works quite like this atomic clock. But it gets all the main operating principles in, and all atomic clocks work in this fashion. And ours is going to be a cesium atomic clock, but it doesn't have to be. Atomic clocks have been built using strontium They've been built using rubidium, which is very common. The first ones were built using hydrogen. But cesium, as we shall very shortly see, is the gold standard for making an atomic clock. Okay, you guys happy so far? You believe all this? Okay, all right. So my atomic clock is going to start off with a vacuum chamber. There's nothing in here except a little hunk of cesium. Cesium-133. And so I guess we better look at some cesium. So in this plastic cube, if you use this because it's very small, is a tiny little glass vial just underneath the word cesium. And in that glass vial, you can barely see sort of a straw-colored material. That's actually metallic cesium. Cesium has some useful properties. Number one is it has a resonant frequency, which is what we call the frequency that the element will absorb and reemit. It has a resonant frequency that we find it fairly easy to deal with. It's not too high, it's not too low. It's pretty easy to generate microwaves. This is in the microwave region. In fact, I think police X-band radar is right around this area somewhere. Okay, so we're kind of used to doing that. It has another useful property that has a very low melting point. It's about 83 degrees Fahrenheit. So in here, in the air conditioning, it's solid, but if we took it outside on a nice day, it would very quickly turn to liquid. And it has an unfortunate property that's pyrophoric, meaning it burns on contact with air and explodes on contact with water. So don't bust this open. If you break this open, you're going to be on your way to having a really bad day. But this vacuum chamber has nothing in it but a little bit of cesium. And my atomic clock is going to have some heating elements around it so that we can melt this. And it doesn't take much power to melt it because it melts really easily. Okay. And on my atomic clock, I'm going to put a, see, I'll put it up here, I guess. I'm going to put a semiconductor laser. And I'm not a hardware guy, so I imagine they sort of look like something out of the Forbidden Planet, okay? And this semiconductor laser is going to be tunable. It's going to be tunable just on either side of this frequency, in a range just on either side of it. And it's going to be controlled by an oscillator, which it might not, it's probably not the oscillator out of your wristwatch, but I'll draw it as if it is. And this is a tunable oscillator. By changing the voltage that we put across it, we can change within a narrow range on either side of this. We can change its frequency, and its frequency controls the frequency of the light we emit here. And I'm going to put a little controller here so that we can tune this oscillator. And I'm going to imagine this is like an old-timey radio with a dial here and a knob. Okay. And so I can actually tune the frequency of the photons that come in the coherent beam, the laser beam, that shoots straight down into the vapor that is the cesium. Because it's in a vacuum, it not only melts to a liquid, but it very quickly becomes a cesium vapor. So there's just cesium atoms flying all over the place, hither and yon, okay, inside this chamber. And now here's the really cool part, okay? So brace yourself. I'm going to put a photon detector over here, which I've actually used photon detectors in embedded projects, but I sort of imagine they look like a big eye. And that's my atomic clock. Because what happens is I tune the oscillator, and therefore the frequency of light coming out of the laser back and forth until I hit the resonant frequency of cesium. At which point, all of these atoms in this vapor absorb and re-emit the photons that are in this coherent beam going straight top to bottom. But when they emit it in any direction, including into the photon detector. So I'm going to simply tune the oscillator and therefore the laser until I see the maximum amount of energy coming out of this photon detector. And at that point, another wonderful thing has happened. Okay? This oscillator, this simple, humble oscillator, is running at the resonant frequency of cesium. And it turns out that if you have an oscillator running at the resonant frequency of cesium, and you count off 9,192,631,770 beats of that oscillator, that is the definition of 1 second, the standard definition of 1 second in the International System of Units. So now you have a frequency source from which you can derive the length of 1 second that is by definition correct. That's pretty exciting. Of course, it's not that simple. It's not that simple because if we were to, what we would like is if we plotted the energy seen by the photon detector with the frequency that we're emitting, what we really want is we want this graph to look like this, right? Where this is the resonant frequency of cesium. But, here's a quiz coming up, brace yourselves. Some of these atoms in the cesium vapor are flying all over the place. Some are flying toward the laser, so they see a higher frequency. And the ones flying away from it see a lower frequency, and that's because, come on, the Doppler effect. And so, this graph looks more like this. But that's okay, because on average, it's still pretty darned accurate. And in fact, the difference between a $50,000 commercial cesium atomic clock that you can buy, you can actually buy one, put it on your lab bench, mount it in a rack, equipment rack, or the one that you go to NIST and see, the F2, which is like the frequency, central frequency source for the whole US. The difference between those two, between a multi-million-dollar one that requires a whole team of engineers, technicians, and scientists to keep it running, and one that you can actually just buy and sit on your lab bench, is all the extra hardware you need to make this graph narrower and this peak higher. But in fact, even the commercial models are still the best things in sliced bread in terms of accurate frequency source, because you are not likely to have an instrument that can actually measure the jitter in this, because you would have to have an oscillator in your oscilloscope better than the one that is the atomic clock, and you're not likely to have that. Okay, so even though you get some jitter, you're probably actually, if you try to measure, you're going to be measuring the jitter in your oscilloscope oscillator, not the one in the atomic clock. So you can actually buy used commercial atomic clocks on eBay. I confess, I've looked. Okay, they're about 15 grand for ones that I think probably work. They're actually quite common, but they're a little big, and they're a little expensive for me, because what I would really like is I would like to add an atomic clock to this clock. And the way I would want it to work is I want to be able to use GPS to synchronize my atomic clock, phase lock my atomic clock to the cesium atomic clock in the GPS satellite. And then if I lose the GPS signal, I want to just go into holdover and use my free-running cesium atomic clock, because it's still the most stable frequency source I'm ever likely to own. And I'll simply use that to keep telling time, to tell when a second has passed. And then when GPS comes back again, I can check my synchronization with my clock and rephase lock it and so forth. But that would be really cool. The 15 grand is just a little bit out of my price range. But fortunately, around 1990, the physicists at NIST, same place right up the hill, their job is time, okay? They made a breakthrough in miniaturizing the parts of an atomic clock, and down to where you could use semiconductor manufacturing techniques to actually build a cesium atomic clock. So it went from being about the size of a small suitcase to something that you could actually mount on a board, and they called this a chip-scale atomic clock. So DARPA in the 2000s thought this is the greatest thing since sliced bread. An excellent question would be why was DARPA so interested in this. They thought this was the best thing since sliced bread. And so they actually funded 2 separate programs to commercialize this CSAC technology. And that happened. And in 2011, a company called Symmetricon which had already purchased the entire commercial atomic clock business from Agilent, formerly HP. So they were already making the suitcase size desktop or lab benchtop atomic clocks, cesium atomic clocks. And since they've been bought by Microsemi, so you'll see Microsemi, which is a semiconductor company all the hardware guys know about, you'll see them talking about atomic clocks. So Symmetricon came out with a chip-scale atomic clock. You could actually buy these guys. And a company called Jackson Labs Technologies said, wow, that's a great idea. I bet a lot of people are going to want one of these integrated with a GPS receiver that has an ARM microcontroller to do the phase lock of the atomic clock to GPS time, and then just keep generating timestamps based on the cesium atomic clock when GPS isn't available. And so that's exactly what they did. And so I had to buy one of those too. And so that's this generation. And so this clock and this clock are actually almost the same. This has got the same model Raspberry Pi. It doesn't have the GPS receiver because I don't need it on this one. But it's got a, it still has the real-time clock with the battery backup and the LCD display. This little metal can here is the Microsemi chip-scale atomic clock. That's an actual cesium, miniature cesium atomic clock. It's got an ARM microcontroller that handles all the external interface. It's got a U-Blocks GPS receiver that goes to an antenna over there. Let's see, did we ever pick up any? Nope, still zero. Still not picking anything up. This works fine at home. But it works exactly the way you would want it to. It phase locks the GPS clock, or the cesium clock, to GPS time. And then I've disconnected this for days at a time. And I run Network Time Protocol daemon on this, which compares its clocking to other NTP servers with atomic clocks on the internet, and it never tells any difference. Okay, I run it for days on holdover without a problem. And so this is an actual, this is a mantle clock that sits in a big Lexan box in my living room to keep the cats off of it. So this is the most accurate clock I own, or indeed am ever likely to own. Okay, this is my very own cesium atomic clock. Okay, now I'm ready for questions.
There's called standard deviation of your frequency curve versus the standard deviation of the time calculation that you're getting from GPS and your volume of 15 meters. How do those two compare?
Let me see if I can answer that. The resolution of GPS time is actually really good. It's about 1.5 nanoseconds, I think. That's how closely the GPS clocks are synced to the ground clock. I'm not sure I can answer exactly that question, but let me see if I can work my way around to it. The atomic clock at NIST is accurate to a few nanoseconds a year, but this clock is accurate to a few microseconds a day, so it's not nearly as accurate. It's good enough for the things I want to use it for, but it's nowhere nearly as good as the big atomic clock at NIST that's like the size of several refrigerators side by side.
Well, that's pretty close to nanosecond time right there, so if you're off by
Yeah, but remember, speed of light, a nanosecond is about 11 to 12, a little bit over 11 inches. I always think of it as a foot, but it's not quite a foot. So you don't have to be far off, but GPS is only accurate, guaranteed to be accurate within about 15 meters. And on a good day, depending on the geometry of the satellites that you can pick up, you can get down to 8 or 9 meters. But it's still, you know, it's 24 feet, so we're talking 24, 25 nanoseconds, something like that. It's still at time and space. It's still better than anything I'll ever own. So, man.
Do you know what speed or impulse you need to actually have relativity problems?
Actually, the GPS satellites have to have their atomic clocks adjusted for relativity. They actually, I believe they have to, actually, I'm hedging on this because relativity affects them in two ways. They're further away from the mass of the Earth, which makes them run faster, but they're an accelerated frame of reference due to their orbits and their centripetal acceleration. And so that slows them down, and I think the net effect is they're slowed down. So they actually have to be adjusted faster than the ground clock in Colorado Springs. But I'll just jump ahead a little bit and tell you why DARPA was interested in this, because it has to do with your question. There's a lot of uses for these chip-scale atomic clocks. Number one is, obviously, you can put them in a GPS receiver, and if it loses GPS, it's so stable that the amount of iteration it has to do to converge on a solution is virtually zero, right? Because when it gets GPS back again, it will be already almost synchronized with GPS, or it will be synchronized. The other one is, you guys would know more about it than I do, but wireless network technologies that have air interfaces that use frequency division multiplexing have to put guard bands in the spectrum between channels because the oscillators and the transmitters aren't that good. If you had a miniature cesium atomic clock in your transmitters and receivers, you could make those guard bands a lot narrower and make more efficient use of spectrum, okay? But the real reason, and the one why I'm talking about this now for you, is you can, relativity, as you just pointed out, tells us that time slows down in accelerated frame of reference, and that's detectable with an atomic clock if you compare it with one outside the accelerated frame of reference, which means you could use a cesium atomic clock, but because acceleration can be centripetal acceleration, or centripetal acceleration, linear acceleration, but it can also be acceleration due to gravity, and gravity is a property of mass. So you can use a cesium atomic clock as a mass detector, which is sort of the opposite of what you were asking. Right there, you're actually leveraging the change in time. And making a small portable mass detector that you can economically blow up is of interest to people, oceanographers and geologists, or anyone looking for a submarine or an underground bunker. Okay. So these things are accurate enough that they can actually detect changes in mass. I've got about one more minute. You know, one thing I didn't talk about was radio clocks. At home, my wife and I have this clock on our TV that's just a big LCD display, okay? And at the bottom it says atomic clock. Well, it's not really an atomic clock. It's more properly called a radio clock. It actually picks up a digital radio signal from a radio station in Fort Collins, WWVB. It's a long-wave signal, 60 kilohertz, I think, is its frequency. And it sends out, and it's synchronized to an atomic clock at the radio site, the transmitter site, which is run by NIST, which in turn is synchronized to the atomic clock in Boulder. And you can buy quite accurate clocks, and they can be quite small. This wristwatch is a radio clock. It actually receives the WWVB signal and sets itself every night. And so it's not an atomic clock, but we like to say in the computer world and in the world I run around in, telecom world, its time is traceable to an atomic clock. So, any other questions? Yeah.
Is Boulder backed up?
Yes, there's an F1 and an F2. But F2, I think, is the active one right now. But there are two master atomic clocks. Now, remember when I said all this extra hardware you need to make this? Well, you know, you can go on Wikipedia and read about the old atomic clocks. It all had to do with one of two things: either making the cesium or hydrogen or whatever you're using, making those atoms fly at right angles to both the microwaves and the detectors, so you didn't get a Doppler effect. Or the newer ones actually use cryogenic techniques like lasers pushing all the atoms into a little bundle in the middle of the vacuum chamber and trying to keep them from moving. But the Naval Observatory near Washington, D.C. had a completely different approach, because this jitter is completely uncorrelated between different clocks, because it really is random. It's Brownian motion, right? And so they have an ensemble of atomic clocks. It's a wall of commercial atomic clocks. Rack, 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 clock, 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 and they just average them all together. And I think that's really clever. So, I hope to do that one day when I'm in the lab, is have a wall of atomic clocks. Okay? Has this been okay?
Yeah.
Did you like it?
Sounds like you have too much time on your hands.
Well, thanks a lot. That's it. And thanks a lot for GoGo for sponsoring.